Good day, I am Jake Avila. Today we will introduce additional integration rules involving trigonometric functions. And in the second part, we will tackle the concept of a definite integral and explore some rules on how to evaluate these integrals. So let's start. We start the lecture by recalling what is an antiderivative. Here, we call capital F of x an antiderivative of a function f of x if the derivative f prime of x is exactly your function f of x. Moreover, we have seen that we can rewrite this using the integral notation as the integral of f of x dx is capital F of x plus some constant c. So let's apply this in obtaining the integrals involving trigonometric functions. So let's recall the derivative of the 6 trigonometric functions. First, we have the derivative of sine x is cosine x. So in terms of the integral, we can rewrite it as the integral of cosine x dx is sine x plus some constant c. Next, we have the derivative of cosine x is negative sine x. So in terms of the integral, we have the integral of negative sine x dx is nothing but the cosine x plus some constant c. But we will be rewriting it as follows. So yung negative ilalagay lang natin dun sa indefinite integral. Again, this is the same as negating the right hand side. For the constant, it will also be negated, but we will just keep it as plus c. Wala rin naman problema. So here we have the integral of sine x dx is negative cosine x, and then just retain plus c. So next we have the derivative of tangent x is secant squared x. So in terms of the integral, we have the integral of secant squared x dx is tangent x plus some constant c. And for the last three, we have the derivative of cotangent x is negative cosecant squared x. So we have the integral of negative cosecant squared x dx is cotangent x plus c. Again, we put the negative on the indefinite integral. So we have the integral of cosecant squared x dx is negative cotangent x plus c. Next, we have the derivative of secant x. So this is secant x tangent x. So we have the integral of secant x tangent x dx is secant x plus some constant c. And lastly, we have the derivative of cosecant x, which is negative cotangent x cosecant x, or negative cosecant x cotangent x. So we have the integral of negative cosecant x cotangent x dx is cosecant x plus some constant c. Again, we put the negative on the indefinite integral, so this becomes the integral of cosecant x cotangent x dx is nothing but negative cosecant x plus c. So for now, let us try to memorize the 6 integration formulas for functions that involve some trigonometric expressions. Okay, let's try to apply this integration formulas in the following examples. So first, let's have the integral of secant x, secant squared x plus 2 over secant x dx. So here, our strategy is to first distribute the integral sign. So we have the integral of secant squared x plus, and then factoring out here 2, we have 2 times the integral of 1 over secant x dx. For the integral of secant squared, we don't have any problem because this is just tangent x. So we just rewrite it as follows, dx, don't forget, and then plus 2 times the integral. For 1 over secant, we don't have any formula, but let us recall that 1 over secant x is just cosine x dx. So now we can directly apply the formulas that we have obtained earlier. So we have the integral of secant squared dx is just tangent x, and then plus 2 times the integral of cosine is sine x plus some constant c. So ayan na, no? Next, let's have example number 2. Here we want the integral of secant 4x times tangent 4x dx. Here we have a product of two functions, but we have an integration formula, say for the integral of secant x tangent x dx. This is secant x plus some constant c. So we have this formula earlier, but we cannot directly apply it here and say produce the integral to be secant of 4x plus some constant c. Hindi pwede, no? Dapat kung ano yung nasa loob, variable lang, no? Dapat x lang, hindi pwede 4x. So para magawang variable yung nasa loob, we introduce a substitution. So we let u equals 4x, so the differential du becomes 4 dx, and then we rewrite the given integral. So we have the integral of secant 4x tangent 4x dx to be, in terms of u, it is the integral of secant u tangent u, and then your dx, from here you can solve dx, so your dx becomes du over 4, so times du over 4. In this one we can easily integrate, so we factor out first 1/4, then the integral of secant u tangent u du. For this one we can now use the formula kasi variable na lang yung nasa loob. So we have 1/4 secant u plus some constant c. And again, just like the previous lesson for the substitution rule, ibabalik lang natin sa x using the substitution u equals 4x. So the integral of secant 4x tangent 4x dx is nothing but 1/4 of secant 4x plus some constant c. Next, let's have example number 3. For this one, we want the integral of 3x squared times cosine of x cubed plus 1 dx. Here we have a product of two functions. So to introduce a substitution, we look at the more complicated expression. So here, comparing the two, the more complicated one is cosine x cubed plus 1. And for the substitution, the innermost function is x cubed plus 1. So we let u equals x cubed plus 1. So your differential du is 3x squared dx. And when we look at our integral, nandyan na lahat, no? So rewriting, we have, pwede natin mapalitan ng u ay yung may x cubed plus 1. So we write that first, cosine x cubed plus 1, and then ang matitira ay 3x squared dx. But thankfully, this is exactly your du. So you can now rewrite it as the integral of cosine u, and then your 3x squared dx is just du. So the integral of cosine u is sine u plus some constant c, and then putting back to x, we have sine of x cubed plus 1 plus some constant c. Okay, next let's have example number 4. Here we want the integral of 3 cotangent of 3x times cosecant squared of 3x all over 1 minus cotangent of 3x cube dx. So, medyo komplikado, no? So, just like with our previous lesson for substitution, we just look at the integrand and spot the most complicated expression. So, we compare, is it 3? Is it cotangent 3x? Is it cosecant squared 3x? Or obviously, is it the denominator? So, here we can see that the most complicated expression is your denominator, and the innermost function is 1 minus cotangent 3x. So we let that as our substitution. So we let u equals 1 minus cotangent 3x. So your differential du is 0 minus the derivative of cotangent 3x. So let me just write that down. So the derivative of 1 minus cotangent 3x dx. So from here we have 0 times negative, and then the derivative of cotangent is negative cosecant squared of 3x, and then by the chain rule the derivative of 3x is 3, and then dx. So simplifying, we get negative times negative becomes positive, and then putting the 3 before cosecant, we get 3 cosecant squared of 3x dx as our differential du. So now let's look at how this will change or how this will transform the integral. So here, isulat muna natin yung pwede natin mapalitan agad, no? So since u is equal to 1 minus cot 3x, yun na muna yung isulat natin na pwede natin palitan, yung denominator. So 1 minus cot of 3x, then cube. And then sa du, kailangan natin ng 3 cosecant squared 3x. So from the original given, kukuhanin natin si 3 at kukuhanin natin si cosecant squared 3x, and then we will multiply that with dx. So here we just put 3 cosecant squared of 3x and then dx. Okay, and then what is left is just this factor. So we have cotangent of 3x. So now, yung denominator, pwede na natin palitan ng u cube, and then this expression, pwede na natin palitan ng du. Ang natitira na lang ay paano natin mapapalitan ng u ang cotangent 3x. So again, looking at this substitution, we can solve for cotangent 3x. So cotangent 3x from here is what? It is 1 minus u. So we will use this para palitan yung cotangent 3x. So doing so, we have the integral, and then cotangent 3x is 1 minus u, and then the denominator is just u cube, and then this one is just your du. So for the integral of a quotient, we divide each term. So we have u raised to negative 3, so that's 1 over u cube. And then for u over u cube, you have 1 over u squared, or u raised to negative 2, and then du. So using the power rule, we get what? We get negative 1 over 2 u squared. So I'll just leave this to u, plus 1 over u plus some constant c. And then finally, we put back to x using our substitution. So this becomes negative 1 over 2 times 1 minus cotangent of 3x squared plus 1 over 1 minus cotangent 3x plus some constant c. Okay, let's move on to the next lesson. Here we consider the graph of the function y equals f of x in the first quadrant. So here on the positive x-axis, we choose two distinct points whose x-coordinates are x0 and x3. So our goal is to find the area of the shaded portion in the figure. So here we want the area below the function y equals f of x between x equals x0 and x equals x3 and above the x-axis. Notice that if the shaded region was a polygon, we can easily find its area using basic geometry. But here, the above portion of the region is curved. So how are we going to calculate its area? Our general strategy is to calculate the area of the region is to divide the region into smaller sections. So for the divisions, we choose two equally spaced points between x0 and x3, and we name them as x1 and x2. Here, we notice that x1 and x2 divide the segment from x0 to x3 into 3 equal parts. Now, if we draw these three rectangles over the required region, we see that the sum of its area approximates the area of the region that we want. Here, the region is identified by the red line. In this illustration, we denote by A1 the area of the first rectangle, A2 for the second, and A3 for the last. So the region that we want has area approximately equal to A1 plus A2 plus A3. So all is left to do is to find these individual areas. For instance, for the first rectangle, here for A1, we know that the area of a rectangle is width times height. For the width, it is x1 minus x0, and this difference we will call delta x1. For the height, note that the upper side of the first rectangle intersects the function, say at the point whose y-coordinate is f of c1. Here, c1 is a point between x0 and x1. So the height of this rectangle is f of c1. So this implies that the area A1 which is height times width, is equal to f of c1 times delta x1. So in the same way, we can calculate the areas A2 and A3. So for A2, it is f of c2 delta x2, where f of c2 is the point indicated, and delta x2 is x2 minus x1. And finally, for A3, it is f of c3 times delta x3. So as a sum, we can rewrite A1 plus A2 plus A3 as the sum from I equals 1 to 3 of AI. And each AI we can write as f of ci delta xi. Now we go back to our original goal. Here we just renamed x0 to be A and x3 to be B. So from these approximations, how can we get the exact area of the region? So let's have the following observations. So for n equals 3, we saw that the approximation is A1 plus A2 plus A3. So now, compared to the exact area, there might be some excess because of the portion of A3 exceeding the region. Now, for n equals 4, or here we have 4 rectangles instead of just 3, we can see that the approximation is given by A1 plus A2 plus A3 plus A4. And this approximation is more accurate than the previous one, so when n equals 3, since A3 and A4 now have less excess in the area. Now, let's see what happens when n equals 6. So here, the approximation is even better, meaning there is way less excess in the areas. So it appears that as n, or the number of rectangles, gets larger, the approximation becomes better, and the width of each rectangle becomes smaller. So this gives us the idea that when n goes to infinity, the width of each rectangle approaches 0, as if we are just drawing straight lines from the function to each point in the interval a to b. So we get exactly, or we sweep exactly the area of the required region. So if we have n rectangles, the approximation of the area is the sum from I equals 1 to n of ai. And if we want n to be larger and larger, we take n going to infinity. So formally, the area under the curve y equals f of x from x equals a to x equals b is the limit as n goes to infinity of the sum of the areas ai from I equals 1 to n, with each ai equal to f of ci delta xi. This limit we will write as the following symbol. This symbol we will read as the definite integral of f of x from x equals a to x equals b, or simply from a to b. Here, a is called the lower limit of integration and b the upper limit of integration. So from this definition of a definite integral, we see that since it is interpreted geometrically as an area, then its value is always a number. So maybe that's why it's called definite, compared to the indefinite integral, which is a family of functions. Now, a natural question at this point will be, how can we compute for the value of a definite integral? So do we need to compute for an infinite limit of a sum all the time? Or is there a more convenient way to do it? So another observation is that the definite integral shares almost the same notation with an indefinite integral. So must the two have any connection? So we will address these questions in the next video.